Alright, hello folks. So today I'll be starting with linear regression, and this is the series of machine learning. Okay, so let's get started. I'll take a simple problem. You have been given a set of points in the 2D plane. So the set of points I have given it as this xi, yi, and I goes from 1 to n. So that set that is this has been called as dn. So it is n points, and this is your data. Let's just plot it, and in this case I have made it such that it looks something like this. So this is your set of points. It looks something like this. Now what the problem is to find some corresponding y value for an unseen x value. Okay, so your query is given an x which is unseen. It will most likely not be in your data set, and your goal is to find a y hat, and this y hat will be your symbol for any sort of predictions from now on. And you have to find a y hat which is an appropriate y value for an x. So what is the appropriateness and all these things, we'll take a look at that. So before that, I just want to say that this is a generalization task, because what we are doing is finding some sort of structure in the data. We're finding some sort of structure in this, and given some new value x, we want to find the corresponding y value wherever it may be. Okay, so let's move on with the 6 steps. First is problem formulation. So based on the data set dn, figure out the best candidate of the y value for x which is not in dn. I mean, it can be in dn, but let's just assume for now that it's not in dn, because that will be the most likely case that you'll encounter in real life. Now the assumptions that I'll be making on the data is that the generation process for each of these points in dn is similar, if not the same, and the generation of any of these points is independent of the other. So whatever points I have generated over here, whatever their process of generation may be, maybe you're using a computer to generate random points like this. So something like that, whatever the generation process might be, every point generated is independent of the other. So they are independently generated. It's not like if this point is generated here, so that will imply that the other point, this point has to be generated here, or that will form a chain of events like that. No, nothing of that sort. If this point has been generated here, all the other points are independent of it. Nothing like, no correlation between those points whatsoever. And now the evaluation metric. So if I'm predicting y hat and my actual value is y, now how will I judge the quality of y hat? So in this case I want y hat and y, these two things. So if this is the actual point, this is x y, and x y hat lies somewhere here. So I want these 2 points to be as close as possible, right? That's the whole business. Like, you want your y hat to be as close to y as possible, and so to encode that, this is your evaluation metric, and this, by the way, is called the squared loss. So what it does is it essentially minimizes the Euclidean distance between y hat and y. So y hat is our guessed and y is the actual thing. Between those two, they're minimize the distance, and that's why we have this sort of evaluation metric. Alright, and y hat, obviously it will be a function of your x, and that's a given. Okay, modeling now. So modeling is basically finding out a suitable prediction function that takes in x and gives you a y hat. Now what sort of mathematical form will it take? Okay, I mean, this is visible now, what sort of mathematical form it will take, but why have I even chosen this? Why can't I choose something else? I can choose something like w0 plus w1x plus w1x square ... keeps on going, right? I can choose something like that. Why have I chosen this particularly? So this is where, the more human aspect of machine learning comes in. Again, this is also a very human aspect, because I mean, a machine won't be able to think that, okay, I have to minimize the distance. I mean, machine won't be able to say that. So even the modeling part, what sort of model I have chosen for this, it's because I see that, okay, like in this particular case, however, and because for convenience, the points I have plotted here, they look like, okay, they almost fall into one single line. So what is that line? That's the point, right? So if I have to predict a y value, then it has to be some mx plus c. So that c and m, they are parameters. I want to tune that c and m so that I get a best fit line, basically, that fits into the data. It's pretty close. Now, how I determine that best fit line, that's what we'll be seeing, and this loss metric, it will play a role in that. Alright, so we have determined our y hat to take a mathematical form of w0 plus w1x. Now, the learning algorithm. Okay, so that's what this learning algorithm does. It searches through w0, w1 and finds the best pair. And how do we choose the best pair? Well, there is one way. There are actually many ways to go about doing this. Like, how do we choose the pair that gives best performance measure across all the data points? So, I mean, you cannot give best performance across all data points. Okay, let's get that straight. If you minimize the loss for one data point, then you will obviously be increasing the loss function for all the other data points. So you have to find some sort of balance between all those n data points. Okay, I mean, you cannot just give all the minimized loss to one data point. So that's the whole problem here. Okay, but how do we exactly go about doing that? What do we exactly minimize? So let's minimize this. Let's say there are many ways to do this, but let's minimize this. This is basically average of all the losses. So L, as I said, it's basically the squared loss. And what I'm doing here is for every training point, I'm defining a squared loss. Obviously, that will be 1. And I'm taking the average of that squared loss, which I'll denote by this capital L. I'll show you what this W bar means in a moment. But clearly, this whole average loss, it depends on your data set. It depends on your data set. And we are taking the mean of all the squared loss over this data set. Now, this W is basically, I've written W1 and W2 collectively, W0 and W1 collectively as a vector. Okay, and that's what this is. Now, you have to minimize this. So if this were a 1D problem, then you will just take the derivative, and if there were no W1, let's see, if there was just W0, suppose this is not existing now, there is W0 and Y and Yi. If something were like that, then obviously you will just do dl by dw0 equals 0, and then you will solve for w0, right? Well, in multiple dimensions, then you have to take the partial derivatives, and the partial derivatives will have to be set to 0, and you will basically find something like this. All right, so this is what you will do. You will take the partial derivatives and set them to 0, and that's okay. That's simple. It forms a system of equations. They look something like this. So okay, this is partial L by partial W0 going to 0. You get a system of equations like one equation like this. It's an equation on W1 and W0. Okay, and similarly for partial L by partial W1, another equation on W1 and W0, and you solve them. I have done some calculations. I was too lazy to calculate W0, so that's okay. But again, very tedious, right? And yes, machine learning is tedious. This is the low level calculations that go on when you do machine learning, but we can actually make it much more intuitive, or at least much more easier. The calculations can be much more easier provided we have a knowledge on a few things like vector calculus, matrix derivatives, all these things, which will come in the next few lectures. Okay, in the next lecture, my job will be to explain to you how we can vectorize this stuff. And by vectorizing it, I mean making the whole set of equations compact, and so that we can use vector calculus on them. Okay, with that, I'll stop the lecture right here. Thank you, folks. See you next time.